tissue. Is it on? Okay. In this talk, I will at first give a motivation why we are interested in describing the cardiac tissue with a different approach than has been carried out before. I will describe shortly the motivation in direction of fibroblasts, as this might be another domain. Come to mono and bidomain models, which have been the established approaches for modeling. The multidomain model that I will describe here is somehow a straightforward extension of these models. I will formulate it in a mathematical manner, then give some insights in the derivation of conductivities which are necessary for this approach, give a short introduction to the mathematical formulation, how it can be solved, and then present some results and draw conclusions, give some insights in limitations that we found while our approach was worked out, and give a perspective. Most of you are aware that cardiac tissue is not just consisting of myocytes. They are somehow the dominant cell type by volume, but there are quite a lot of others. For instance, fibroblasts, which are the dominant type by number. And we also know that there are endothelial cells, smooth muscle cells, and neuronal cells. The ratios of them, the numbers and the volumes of them change for different tissue types. They change over time in development. It's different among species, and in disease there's can be a traumatic change. However, most models up to now have somehow a myocyte-centric point of view. They prefer to model the myocytes to describe the cardiac tissue. What we want to introduce here is a model which allows to describe cardiac tissue as a composite of quite a lot of cells. We want to describe also the extracellular space in such a manner that we can measure extracellular voltages and currents which flow there. And we make one example that's with respect to fibroblasts, which I will show here. That's probably let's start with the fibroblasts from the point of electrophysiology. It is well established that fibroblasts can be coupled to myocytes. They are nevertheless inexcitable, means they have no sodium channels or calcium channels in a significant amount. It's mostly potassium channels, so they are completely unexcitable. It is also well established that fibroblasts can couple excitation from one myocyte to another one over a distance of around 300 micrometers, which is a quite significant length. This slide here below shows myocytes and fibroblasts. Green is here the myocyte. The actin is here stained. The blue one is the fibroblast. The DDR2 receptor is stained. And it might be tough to see these red dots here. They point at gap junctions, connexin 43, and the arrows here point at those gap junctions which are associated to fibroblasts. Some years ago, we developed an electrophysiological model of fibroblasts, which is shown here. The physiology is rather simple. It's mostly a Keir current, a shaker current, somehow a background current, and then a stimulus current. The voltage current relationships here measured, that's the Keir part, that's the shaker part, and this is what the model here reconstructs. From an electrophysiological point of view in comparison to myocytes, it's really a simple description. When looking at myocyte models, there are magnitudes of orders more components involved. I hope that I can skip this slide, that someone would introduce the bidomain model. I think you saw some illustrations of the monodomain model, which somehow has resistor here in a resistor representation, coupling the intercellular space. The bidomain model adds here another resistor network to the extracellular space. That is a description somehow for electrical engineers coming from resistor capacitor circuits. There are other representations possible, which we also used for our model derivation. That here shows roughly our model. That's the myocyte domain, that's the extracellular domain, and what we add here is a fibroblast domain. It's fully coupled, means that we can have currents from the fibroblasts to the myocytes. We have also these intracellular domains then coupled with conductivity tensors. It should be rather straightforward to extend this to an n-domain model. I know that others said this before, and their proof finally needed around 400 years to be done. Here it's just a question of matrix formulation that we can go to a 4-domain or 5-domain or other domain of model. Just to fill this a bit with the equations, again, here are the myocyte, fibroblast, and extracellular domain. This here are the Poisson equations associated to those domains. That's the definition of the voltage here as a difference of extracellular and intercellular potentials. We have here the ion channel models hidden. This describes the current which can flow from the fibroblast to the myocyte domain and the opposite direction. And again, we have here a Poisson equation which needs to be solved to get information about the extracellular voltages. The mathematical formulation of the conductivities is shown here. That somehow it was already a difficulty for the bidomain model to extract conductivities. Here we increase somehow this complexity because we have another domain. We need to make a further assumption. What we used here is we assumed that there are 20% of the space extracellularly, and then we define rules depending on the number of myocytes, how the conductivities can be transformed. It is done here in a somehow first order approximation just by scaling via the volume ratio. This is the volume ratio of the myocytes, that of the fibroblast. This conductivity tensor would be if everything would be filled out, the whole space would be filled out, and then we just calculate this from the ratios. This table here depicts the values. We took the raw conductivities for the bidomain part from Roth, the publication in Circulation 91. This here gives information on how we solved this tri-domain model or 3-domain model. We calculated first extracellular voltage densities, current densities, then calculated the extracellular potential, and then solved for the different cell types. Here we used in the simulations the Pandit model, and for the fibroblast model, what I've shown before. It's a time-stepping method. It's a rather straightforward approach. Here are some results of simulations that in a 1D strand addressed the voltages. It is obvious that the myocyte somehow drives the fibroblast. That's after 9 milliseconds. We see a wave. That's the voltage, transmembrane voltage of the myocyte, followed somehow by the fibroblast. And here is repolarization. We ran these simulations with different conductivity values, one approximating longitudinal conduction, the other one transversal conduction. And what we found, and what will be seen later again, is that for transverse conduction, there's a much stronger effect of the fibroblast than for the longitudinal. That's somehow related. This conductivity here is of the myocytes is much smaller than for the longitudinal. That's a 2D simulation, again at one time step. That's the voltage of the myocytes, fibroblasts, and the extracellular space. And what is calculated here is the anisotrope ratio of the conduction velocities. We find that, again, for high fibroblast coupling, that there's a dramatic effect. The effect is somehow increased with the numbers of fibroblasts per myocytes. The more fibroblasts there are, the larger is this effect. And we find quite different phenomena depending on the coupling of the interfibroblast space. When you have a very high coupling, we have this curve here, which shows that the anisotrope ratio is reduced. When you have a small coupling, there the anisotrope ratio is increased. Yeah, what we presented here is somehow a description for cardiac tissue as a composite material. Limitations are clearly with respect to validations. We have up to now not done any experiments in this direction. There are now sources somehow for getting parameters of this model, mostly from tissue culture. Here it's possible to control the number of fibroblasts, myocytes, get mixtures, and express specific proteins so that we can derive conductive tensors. What I really find a weakness here, that's somehow also a weakness of the bidomain model, is the rough approximation of the conductivities. I really assume that in these arrangements that there's a much more complex relationship than the linear that we here performed. Applications of this model can be found in various other simulations, for instance, of the sinoatrial node, where there's also a mixture of cell types, and good cardiac tissue in general is heterogeneous. So there might be really a new model class now to describe cardiac tissue as a composite. Thanks for your attention.
Thank you very much. There's time for questions. Andrew.
That's very nice, Frank. More of a comment than a question in relation to your point about validation. What limited data there are suggests that there could be large species difference in the numerical fraction of fibroblasts, particularly between, say, the rat and the mouse. So
absolutely. Yep.
That could be a good comparison.
Yep. If she asks a question.
Okay, yeah. Mine is more of a sort of philosophical question. Both monodomain and bidomain, to me, don't have a myocyte-centric view. They have a membrane-centric view because you have a flow in one space, flow in the other space, and what's important is the current that connects the two spaces across the membrane.
Yes.
So the membrane is the anchoring point in a way. So what is the difference between your approach and simply representing the intracellular component of consisting of variety of being a heterogeneous component? You can have different ionic models that represent different membrane properties in various places, and different intracellular properties representing the resistance to the membrane flow that accounts for the gap junctions. What is different in these two approaches, or is there a difference?
Should I repeat this? So in a nutshell, in a nutshell, if I understand correctly, you would propose that we just throw all the channels available in one description and have then nevertheless two domains
right.
to achieve.
There is always a membrane and there is always a flow, resistive flow in the intracellular and extracellular spaces. And the membrane flow can be, crossing the membrane, the channels can be different in different locations in your body.
Could I showed two slides where you really see a difference. When looking at the myocyte or the fibroblast domain, there's quite a lag in the response of the fibroblast to what goes on in the myocyte, for the temporal lag. And we saw also somehow a spatial lag in this 2-day. There's quite a different feature on the myocyte at the wavefront, which is not found in the fibroblast.
Well, you cannot represent that by having heterogeneous intracellular space. Is that what you're
I think Craig Henriquez did something similar. He actually combined, or just put it on a backpack, the fibroblast on the myocyte. And I think with this approach, it's not possible to reconstruct or predict the same phenomena as we saw here.
There's a number of hands up. Bruce and then Peter. Maybe if we could be fairly quick.
Yeah, really quick question. I just wondered whether the data which Miraglia and Rur have published gives you any opportunity to actually refine your model. Is that useful for validation what you've got?
In the first publication, which was not using this multi-domain model, we reproduced the data from Rur and also showed that it's possible that excitation can jump over this gap. We were actually looking at reflected re-entry. We hope that it jumps back again. So just using standard approaches, we still can reconstruct this arrangement. That's more a monodomain or a bidomain application than.
Frank, great talk, finally addressing the most important cell in the heart here. Coming back to Natalia's question, Natalia, if you have a shock application and you have two not connected areas, the fibroblasts may capacitively interact with myocytes. I think you would have difficulty modeling that if you only had two domains. Am I wrong?
You know, Kathleen's model, it doesn't have it doesn't have that, and it still represents that. You know, what a tridomain assumes is that you can have current flow from fibroblast to fibroblast to fibroblast only.
Yes, but that is quite possible.
Domain, right?
That is quite possible. In particular, if you had something like a stimulus, you might have capacitive interaction between non-resistively coupled parts of the two domains. So I think there is an interesting element potentially.
But you can have That's another. We shouldn't be. Yes.
We're 15 minutes away from a drinks reception.
It's very thought-provoking.
So maybe it would be best to hold some of these discussions over some lubrication. So we should move on. Frank, thank you very much.